Welcome to our paper Quantum Theory and Application of Contextual Optimal Transport, aka QontOT. My name is Johannes Born and this work was performed at IBM Research. With this paper we are first to connect quantum computing with optimal transport and machine learning. Our work lives at the intersection of three areas. First, neural OT, which is about learning to predict solutions to optimal transport problems through amortized optimization. Next, quantum OT, where we use the principles of quantum mechanics that are governing quantum computers to solve OT problems. And last, contextual OT. Here we produce transport maps conditionally. So for example, we have two distributions, mu and nu, which do not arise in isolation, but they are linked to a context variable ci, such that over an entire data set, we strive to learn a global map t theta, such that t theta of ci push forwarded mu equals nu. Contextual OT is a conditional distribution learning problem, which has been studied with neural OT methods like QontOT and concurrent work at ICML this year. Here we propose an entirely new parametric quantum circuit called QontOT to tackle this task. The core of our new quantum ML algorithm is a previously unreported algebraic link between OT and quantum. We made the following observation. If U is a unitary matrix, then the Hadamard product or the entropy product of U with itself is doubly stochastic. A doubly stochastic matrix, DSM for short, is a matrix whose rows and columns all sum to 1. Permutation matrices are special instances and the identity is the most obvious DSM. Now, DSMs are really fundamental for OT. For example, Marco Couturi used DSMs in the seminal 2013 paper to reduce the computation of optimal transport distances from a linear program to a convex problem that can be solved iteratively with matrix scaling. Similarly, unitary operators are fundamental in quantum. Essentially, any operator for quantum state has to be unitary. Thanks to this link, we constructed a circuit with an inductive bias to parametrically produce DSMs. Such DSMs can then be rescaled to form arbitrary transport plans. This link is very notable because it is currently unknown whether a similarly natural classical approach exists that can produce DSMs parametrically. The conditional distribution learning problem is depicted on the left. We are given an initial distribution μi linked to a context variable pk. We would like to predict the final distribution nu_ik, into which μi develops when exposed to the context pk. We strive to learn a global map t theta such that at inference time we can predict final distributions for unseen context and or unseen initial distribution. Our ansatz, as you see on the right, ingests pk and exploits the mentioned algebraic link to produce a DSM. The DSM is then block decomposed to retain only the right stochastic upper half, which you rescale with the initial distribution to the predicted transport plan. The marginals of this plan are the initial and the predicted final distribution respectively. In comparison to existing approaches for conditional neural OT, QontOT can employ any cost function since it does not rely on input convex neural networks like ContOT. Moreover, it explicitly predicts the transport plan rather than only the marginals, which is computationally more demanding but gives better mechanistic insight into model behavior. And QontOT uses gradient-free optimization like Kobyla or Nevergrad since it is amenable to execution on quantum hardware unlike gradient-based approaches. Here you can see depictions of the proposed circuits to produce DSMs and to embed transport maps. As we prove in the paper, the circuit is a valid and complete DSM producer because it always emits a DSM and every DSM can be produced. The circuit scales logarithmically. Precisely, we need at least 4 times log 2n plus 1 qubits to predict n by n matrices. We also need to collect at least O of n log n circuit shots to fill the entire DSM. Otherwise, the likelihood of empty rows in the matrix is high. More strictly speaking, for satisfactory sampling error, we even need O of n squared over epsilon squared shots. So to make this concrete, with real data like in the Cyplex dataset, we would require 56 qubit and more than 1 trillion shots with epsilon of 0.01. Given that quantum computers operate in the kilohertz range, we use instead data with only n equals 16, which requires 20 qubits and 2.5 million shots. The application we study is from single-cell biology. We predict variations in cell type distributions arising from cells being treated with different dosages of a drug. First, to lower data dimensionality, we cluster the single cells into cell types. The task is then, given an initial cell type distribution, μi, recover the cell type distribution νi induced by a drug given a dosage pi. We first generate ground truth samples with an optimal transport solver. And then we train a parametric quantum circuit to ingest the initial cell type distribution and the dosage pi and predict a transport plan. As you can see in this animation, our quantum circuit can predict transport plans conditionally to drug dosage. We can either keep the cells and vary the dosage, thus testing effects of different treatment options as on the left, or we fix the dosage but vary the initial distribution, thus assessing, for example, which cell type distributions are more resistant to changes. When comparing predicted and real transport plans visually and through their Frobenius norm, we generally observe good alignment. Here we plot the Frobenius distance as a function of dosage for QontOT and a simple baseline which ignores the context. We consistently outperform the baseline here and also in an out-of-distribution setting, not shown, thus demonstrating that we can learn distributions conditional to dosage. As further ablations in the paper show, we can do so for different cost functions. However, when comparing to state-of-the-art classical neural OT, QontOT falls slightly behind in most settings. Note that in this experiment the transport plans have arbitrarily marginal distributions, thus we wanted to test the model with synthetic data where marginals are fixed to be uniform. And this is because in this case we are contextually predicting DSMs, which better reflects the inductive bias of our circuit. This problem, which we will study next, is the contextual version of the relaxed assignment problem. We conducted this experiment on a real quantum hardware and used 24 qubits on the IBM Sherbrooke device accessed via IBM Quantum Platform. The circuit had a depth of 50, used 70 ECR gates and a dataset of 40 DSMs of size 8x8. We did not use error mitigation since we used the sampler primitive, and we performed 235 optimization steps with Nevergraph, which took 13 days. We observed good convergence and found that our 24 qubit hardware result outperformed an 18 qubit simulation. Moreover, in this setting that was most closely reflecting the inductive bias of the circuit, we achieved better performance than all classical state-of-the-art neural OT methods, which were trained with backpropagation. Looking ahead, we therefore believe that the use case of contextually predicting DSMs rather than generic transport plans is the most promising application of our circuit. With this, I would like to thank all collaborators of this extremely interdisciplinary project, and for further details, please check out our paper or reach out via email.